Our second speaker will talk about earthquakes and predictions and so on. So Dr. Jordan is a university professor at the University of Southern California. He's actually the director of the Southern California Earthquake Center, where he coordinates international research program in earthquake system science, which involves over 1,000 scientists in more than 70 universities and research organizations. He's an author of numerous scientific publications, and he received many awards. So the McIlwain and Lehman Medals of American Geophysical Union, the Woolard Award, and the President's Medal of the Geological Society in America. He's a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and the American Philosophical Society. So please welcome me. Help me welcoming Dr. Jordan on the stage. And looking forward very much.
Thank you very much. I want to thank Dr. Moore and the organizing committee for inviting me to speak to you, because I'm the spokesman for a large collaboration of scientists, geoscientists, computer scientists, engineers that are trying to do a better job in forecasting earthquakes and predicting their effects. As Dr. Moore said, this is done within the context of an organization called the Southern California Earthquake Center, which comprises 70 institutions. The 18 institutions shown here are the so-called core institutions, and notice they involve offices of the U.S. Geological Survey, which has the statutory responsibility for providing earthquake information, including forecasting information. But we don't do this work alone, even with 1,000 investigators. We live within this computing ecosystem developed by the Department of Energy, by the National Science Foundation, and these resources have been critical to do what I'm going to try to summarize today. This shows you the number of core hours on the large-scale computers that we use for earthquake simulation. And you'll notice that this year we're going to have something like 362 million core hours. That's 1 million core hours we're burning per day on this type of problem. Now, the question is society getting its money worth? Is it really worth this very large-scale computing to look at the earthquake problem using simulation? And I'm going to try to convince you that indeed it is by actually describing the impact that the work so far has had on society, plus what we think is going to be realized in the near term. So here's an example. Just over a month ago, the Los Angeles City Council passed ordinances that require retrofitting of two particularly dangerous types of buildings, ones with soft first stories and ones that are what are called non-ductile concrete buildings that very easily pancake during earthquakes. I mean, how did this happen? I think we all understand how politically and economically charged these types of expensive programs for improving our seismic safety might be. Well, you can trace this to a report that was commissioned by Mayor Garcetti and a team that was led by Lucy Jones, one of our great leaders in earthquake science. They developed a plan called Resilience by Design that recommended that they strengthen buildings, such as the ones that have now been mandated to be strengthened, but also to fortify the water system and to deal with enhanced telecommunications and to increase the reliability, the resiliency of these major urban systems. How did that happen? Why was that plan convincing? Well, here's what the report says. It says, in evaluating, essentially doing the science behind these recommendations, they relied on the shakeout scenario. The shakeout scenario is an earthquake simulation. Here it is. It was done in 2008. It represented the extreme scale computing of that day. It's a magnitude 7.8 earthquake on the San Andreas Fault that ruptures from the southeast end up to about the middle of the Mojave Desert. You can see from the red colors on this diagram that there is a very strong shaking associated with that earthquake. This particular simulation described that shaking both deterministically up to 1 hertz and then stochastically up to 10 hertz. The scenario included realistic numbers of aftershocks, and then it took these detailed models and asked the question, what will really happen? and it was found that there would be a lot of landslides, of course. Fire following earthquake, we know, is a very dangerous aspect of earthquakes. This particular scenario, it is estimated would lead to over $200 billion worth of direct economic costs, and of course, a long recovery time that would compound those costs. It was not just a simulation that was put out there, but it was actually part of a very large emergency response exercise. And I think what it showed is that the disaster planning that we had been doing up to that time was really inadequate for an event of this scale. For example, the fire department was planning on a Northridge-sized, 1994-sized earthquake, magnitude 6.7, which occupies a much smaller area in terms of the damage. So this scientific basis was, in fact, the basis for resilience by design. Here's an example of a study that was done in the follow-up of that simulation exercise. This is by the Los Angeles Department of Water and Power. As you probably know, Los Angeles gets all of its water resources, or most of its water resources, about 80%, coming in through aqueducts that cross the San Andreas Fault, go through that red zone of high earthquake damage. And so there was a resilience study done by LA DWP. I won't go through the details of that, but it's pretty scary when you look at these details, especially with respect to fire following earthquake and other aspects of the urban systems. For example, the LA sewer system, which accommodates 20 million people, would probably be out for 6 months to a year. You can think about that. Well, much has been learned from this and other virtual earthquakes to improve our resilience and to reduce risk. And it's much better than waiting for the real thing. And these simulations are detailed enough to where it's almost like the real thing, at least in terms of these kinds of planning exercises. Shakeout also led to a major earthquake preparedness exercise, which we run every year. We coordinate this now worldwide, across the country and worldwide. This year, more than, I went backward there. More than 43 million people will participate in the shakeout exercises around the world. And so this was an interesting outcome of that example. So I want to talk about examples of earthquake scenarios that we've developed and the impact those have had, and then some full-scale physics-based hazard models that we have recently derived, which are having, again, major impacts on society. And then finally, I want to talk a little bit about going beyond petascale and what we can do if we have more powerful computational capability. So the basis for this is probabilistic seismic hazard analysis, which is fairly simple, as shown in this diagram. You start with some forecast of which faults are going to rupture. We don't, of course, we can't predict when they're going to rupture, but we do know how big an earthquake they can produce. We know how frequently those earthquakes do occur. So we have something, and we have some knowledge about the time dependence. You then have to be able to model how those waves radiate from the fault to some site you might be interested in, let's say a building site. That requires some kind of ground motion prediction capability, and right now people use empirical ground motion prediction equations. Then you get intensity measures that you can use in your assessment of damage and for making design. Now, we started a program back in 2004 to develop a uniform California earthquake rupture forecast, and we put out several versions of that. The latest version was computed at TAC on Stampede, and that was published about a year ago, and is now part of the 2014 release of the National Seismic Hazard Map. Also, the SCEC ground motion simulations have been used to try to improve those ground motion prediction equations, which are largely empirical. Unfortunately, we don't have enough empirical data to really be able to calibrate the equations properly, and simulation properly done really helps us. Well, what has this led to? Well, these studies have allowed the California Earthquake Authority, which is the semi-private earthquake insurance company within California, to lower their insurance rates by about 1/3 based upon these models. And of course, that has saved California homeowners millions of dollars in expenses, but it's also allowed it's attracted more Californians to the insurance marketplace, and that, of course, helps us to distribute the risk. So these are very important developments. Of course, PSHA, as I mentioned, is currently based primarily on empirical statistical methods, And there are persistent uncertainties that people just have not been able to beat down based upon those very simplified parameterizations. So what we are trying to do is build on top of that empirical base a simulation-based capability that will allow us to use earthquake physics and what we understand of earthquake physics to improve these estimates and to lower the uncertainties. And we need a number of ingredients to do that. For example, we have to have descriptions of the earthquake source. When faults rupture, they don't just rupture in a simple sliding fashion. There's all kinds of cracking and breaking and complexity in that. Describing that is itself a supercomputer problem. We have to have three-dimensional models of the Earth's structure, in particular the sedimentary basins that shake like bowls of jelly during earthquakes, so that we can properly represent the ground motions. That's a very large supercomputer problem. And then if we then have those ingredients, we can then calculate scenarios of future earthquakes. And to do all of this, we have to have efficient codes for doing these different types of calculations, some of them very large, multi-scale, and nonlinear. One of our basic engines is shown here. This is just a finite difference code, but one that's highly optimized on the largest supercomputers. And of course, we need those supercomputers. The capabilities, as they've been increasing, have allowed us for the first time to do some of the work. We just couldn't do it in the past. And so we have Moore's law helping us along here, although we can ask the question of whether that will persist. In terms of our work, we've been catching up with this type of performance, moving our codes onto more capable machines, optimizing those codes in various ways, and we're now beginning to be able to use the largest supercomputers in a very efficient way. I should say that these particular codes do have to carry lots of variables through the calculation in these four-dimensional calculations, and they are, in fact, difficult codes. So here is a result. This shows you a map of California in the Los Angeles region, and this is what the kind of ground shaking from an earthquake, this is not quite the shakeout size magnitude 7.7 earthquake that we began to model back in about 2004. This is what people thought that would do. You can see the band of red of high seismic shaking stretching along the San Andreas Fault east of Los Angeles. We did simulations of exactly this event and got a different answer. You can see that in Los Angeles, much higher shaking than would be predicted by these standard ground motion prediction equations. And the reason is because the seismic waves generated along the fault, the energy gets shoved along the fault as the fault propagates, and then that energy gets coupled into sedimentary basins that transport that energy essentially like waveguides. And you can see that in the simulation in the lower right-hand corner. You can see how that occurs. The map shows you the maximum shaking. You can see seismograms at various points. Notice that at Whittier Narrows in Los Angeles, that energy gets funneled in and essentially amplified by that funneling effect. So that's the type of thing we can learn from simulation. We also did simulations with the fault rupturing in different directions, and look at the difference in these maps. They're very strongly dependent on the direction in which the earthquake ruptures. That raises the question, can we predict which way the earthquake is going to rupture? That's an example of an earthquake prediction problem that's different from the one you're probably most familiar with, namely, when is the next earthquake going to occur? And there are possible methods of doing this, and we are working hard on that problem. But it's certainly shown us that we have to modify our estimates of seismic risk. Now, here's the situation in California. We have this big San Andreas Fault that stretches through the state. And of course, that has hosted a number of great earthquakes, the 1906 San Francisco earthquake in Northern California, and then at earlier times, 1857, 1812, and around 1690, although we have no direct historical record, for the Southern San Andreas Fault. But you'll notice that the Pacific Plate is moving with respect to North America at about 5 meters per 100 years. So you have to have earthquakes that are taking up that strain, and most of those are going to occur on the San Andreas Fault. Well, a magnitude 7.8 earthquake, such as the ones we've had, does about 5 meters. So you would expect those earthquakes to occur about every 100 years. However, if you look at the open interval, the time since the last earthquake, you can see that, well, it's about 100 years in Northern California, makes you nervous, but look at Southern California, 158 north of Los Angeles from where the Fort Tejon earthquake occurred. Near San Bernardino, 200 years. And in the southernmost part, the southeasternmost part, we're looking at over 300 years. So we're very nervous about that last part. You might say it's 10 months pregnant. But another way to say it is that this entire southern San Andreas fault is locked, loaded, and ready to roll. So here is an example. This is the shakeout simulation that I mentioned earlier. You can see those directivity waves coming up along the fault, and then they just take a kind of a half-left turn into Los Angeles and then excite those basin waves, and you can see that excitation goes on for a long period of time. We have scaled those simulations up. This is a simulation now for what we would call a full-scale earthquake on the southern San Andreas fault, essentially from one end to the other, from the creeping section down to Bombay Beach and the Salton Sea. This is one where the propagation starts at Parkfield, California, which is where the 1857 earthquake nucleated, and travels to the southeast. And you can see again, now that we have a region of California much larger in terms of its areal scale. To do this simulation required running on Jaguar for 24 hours. That was the biggest computer at the time. And we were actually able to get in a 24-hour run without checkpointing. It was great. But it demonstrated that we can do full-scale simulations up to about 2 hertz in seismic frequency. Now, that upper frequency limit is very important in terms of the seismic simulation, because that essentially governs the computational costs. Essentially, we are looking at an inner scale that we have to deal with, and of course, you can see the outer scale of the area that's affected by the earthquake is very large. That scale ratio essentially dominates the computational costs. Here is the M8 simulation. You see it break out in Northern California. This is looking at the horizontal motion displayed vertically, but you'll notice a number of things happening. For example, it slows down as it bends around the fault and then speeds up again. Notice that there's kind of a cone-like effect. That's a Mach cone because the rupture has jumped to being super shear, beyond the shear wave velocity. It excites those waves that roll into Los Angeles, couple into the basins. You can see the long residence time within the LA basin, and of course, the more shaking you do over longer periods of time, the worse damage you will do. And in this case, going all the way down to near the Mexican border. Well, those simulations allowed, in going from the TerraShake simulation, first one I showed you, to the M8 simulation, we were able to sort of increase performance by about a factor of 3,000 in 6 years, again, migrating to the more capable computers. And that inner scale, outer scale ratio, as you can see, increases by about the same amount. Well, that's all fine and good to be able to do a single earthquake simulation, but California has lots of faults, over 1,000 faults. And so just simulating 1 or 2 earthquakes on the San Andreas Fault doesn't tell you about the hazard you're going to see at a particular site. You would like to know about all the earthquakes. And so to do that, you have to be able to characterize the shaking from many different types of earthquakes and then essentially multiply that by their probability and do some sort of summation to get the total probability you have of strong shaking. That requires looking at faults that are out, let's say, 200 kilometers away from a particular site, this one in downtown Los Angeles. And so we have developed efficient codes for doing very large ensembles of simulations using what we call seismic reciprocity. That's just the time reversal symmetry of the linear wave equation. And that has led to a type of hazard model we call cybershake. Now, to do cybershake, we actually have to mobilize 4 computational pathways. The first one is to develop the earthquake rupture forecast itself. I talked about the fact that we have done that recently on Stampede, and that has become the basis for the National Seismic Hazard Map in California. Right now, we're using the empirical ground motion prediction equations for the National Seismic Hazard Map, but our goal is to really replace these empirical GMPEs with physics-based ground motion simulations. So how do we do that? Well, we have to have some kinematic description of the earthquake rupture. It has to be put into an inelastic wave propagation code. We might have to deal with nonlinear side effects. That gives rise to some record of the ground motion, the seismograms, and from those we can calculate the intensity measures. However, how do we deal with the earthquake source? How do we specify the kinematic fault rupture? That has, well, so I should say we've implemented the second pathway in the cybershake model, and the first large-scale calculations we did were on blue waters. We've also done a number of calculations on what we call pathway 3, which is the dynamic rupture modeling to tell us exactly how that fault might be breaking. That can be done on a smaller scale. You only have to look near the fault, but you do have to consider the seismic waves because those actually participate in how the fault breaks as the fault propagates. Of course, all of this is being done in a very complex geologic structure with sedimentary basins and deep rocks and mountains and so forth. We have to have some way of representing that structure, and we have to do an inverse problem where we take the observed ground motions and somehow feed that back into our understanding of Earth structure. So that's a data assimilation problem, very large-scale computing problem. We call that full 3D tomography, and that I'll show you some calculations done on Mira. So we're using all of these computational resources to do this one very large-scale problem. So here's what the workflow looks like. We have to bring together all of these pathways. We're essentially trying to work pathway 2, but we need to have the earthquake rupture forecast, pathway 1. We have to feed in the 3D Earth structure, generate meshes. We then have to do wave propagation calculations. For any one site, we can reduce that down to 2 very large simulations because we're using the time reversal symmetry, the seismic reciprocity. But then in post-processing, we have to do many quadratures against all of the different faults and all the different rupture variations that describe the activity of the fault system. And we use right now about 500,000 different types of ruptures per site. So that allows us, gives us seismograms. From the seismograms, we can get various data products. And of course, we want to do this for not just one point, but many points. So you'll notice the little white dots on this map of the CyberShake results, 336 sites in Los Angeles where we've done these very large-scale calculations. And we can put all that together into a probabilistic seismic hazard model. Now, that model requires executing many jobs, 500,000 or 500 million jobs, and we have to use advanced workflow software for that. We use Pegasus. Okay, so here's the result for CyberShake. You can see this is being done now for 2 different models. One is a simple one-dimensional structure, and the second is a 3-dimensional structure, a much more realistic structure, where we're actually satisfying the data we have on how seismic waves propagate through Southern California. You'll notice that on the left-hand side, the map looks fairly simple. There's that big red stripe along the San Andreas Fault. That's because of the directivity pulses that run up and down the fault during large earthquakes. That causes very large shaking, as you saw in some of the simulations. But notice how that red stripe is much smaller and much more intermittent on the full 3D, because that directivity pulse actually is getting scattered by the 3-dimensional heterogeneities. That energy is being taken someplace else, primarily into the sedimentary basins. So it changes the entire seismic hazard map to deal with the full 3D structure. So here is the results of our latest study. This is was done in started in April of this year. It took 38 days. We used both Blue Waters and Titan to take the CyberShake calculation up to 1 hertz in seismic frequency. The earlier maps I showed you were up to about 0.5 hertz. This is obviously a very large workflow. We had up to 42 concurrent workflows running. Well, on average, we had about 42 workflows running during the 38 days that it took to calculate this model. The reason why we believe the 3D model is because of these 3-dimensional structures that we have been able to derive by assimilating data from seismic data, but also other types of data. We use data from the oil industry and so forth, and we obtain these structures. This shows you depth slices through the Earth at 2 kilometers down to 12 kilometers. These models actually go much deeper. But the point is that they themselves require tremendous numbers of simulations because we're doing full 3D tomography, which means we're starting with 3-dimensional models, we're calculating seismograms, we're comparing them with the observed seismogram, we're saying, oh, they don't match too well, let's modify the model in such a way that it satisfies the data. And indeed, we can get extremely good matches to the data. This, in my view, is really revolutionary. I never thought as a seismologist I would see the day where we could get this kind of resolution of Earth structure. And I could spend an entire lecture lecture telling you about the scientific value of these models, of the things we've discovered in the Earth's crust that we didn't know were there before using these techniques. But for the purposes of this talk, the important aspect is that it gives us high fidelity predictions of the ground motions from earthquakes. And we can demonstrate that. Here was an earthquake that occurred in the Los Angeles region, magnitude 5.1, in March of 2014, after we had finalized this model. And so all we did was just simply did a forward calculation, just like CyberShake would do, of the waveforms for this model. These show the low frequency results. The black is data. The red are the synthetic seismograms generated from this three-dimensional model. You'll notice there are places where, and this is to true amplitude, so we're trying to predict the amplitude as well as the phase of all the waves that are coming in. Some of these waves are very complex basin waves that are being scattered in complex ways, but you'll notice a very good fidelity, both in amplitude and even in phase, across the entire seismogram, even out into the later portions of the seismogram where the large surface waves come in. So we believe this type of demonstration validates the type of models that we are using. And so here's what you get when you compare the response of a particular site, and there's two sites here, one in Pasadena, near where I live, and one in Compton, so straight out of Compton, which show you the differences between the GMPs in blue and the CyberShake model in red. Now, this is a particular type of ground motion analysis, and it's exactly what is used for what are called seismic design maps. These are the maps that are used to specify the demands on, let's say, tall buildings that are being built currently in Los Angeles. And you'll notice on the right-hand side that the red curve is quite a bit higher than the blue curve. So in the sedimentary basin where Compton is, the Los Angeles basin, 8 kilometers deep, you can see that there is a very large amplitude difference between the older predictions and the new simulation-based predictions. This has attracted the attention of the Building Seismic Safety Council, which has something called Project 17. And they are interested in using the maps that come out of CyberShake for design maps for the Los Angeles region. And this shows you on the top are the GMPE-based maps. This is using very recent GMPs. On the bottom are the CyberShake maps. You can see that they give comparable answers, let's say at about 3 seconds. If you go out to 5 seconds or out to 10 seconds, the simulation results show much higher ground shaking. And of course, it's very important for buildings such as the ones that are currently being built, the skyscrapers in Los Angeles. So we have the Committee on the Utilization of Ground Motion Simulations going to be reviewing these maps on November 30th, and I expect we'll have recommendations that they be inserted into the BSSC Seismic Safety Design Mapping Program. Okay, here's another issue. What you're looking at here is one of these ground motion prediction equations predicting observed seismic intensities. This happens to be peak ground acceleration. Those are the actual observations of the red dots. The red line is the ground motion prediction model. And you'll notice that these models, which attempt to an increase in the seismic hazard, because if you don't know whether something is going to shake strongly or not, if you can't tell, if you have to account for the uncertainty in your prediction, then that increases your hazard. If your hazard is like these curves, which is the probability of exceeding some particular ground motion level at a particular, for a particular period. So this is in annual frequency of exceedance. And you can see that that variance factor going from 0.4 up to 0.6 causes a couple of orders of magnitude difference in the probability. Now we can take the three-dimensional models, we can do a very detailed averaging type analysis of these models. I won't go into the mathematical details, but we can get uncorrelated variances, not just the total variance that we can compare with the observations, but also we can now partition that into various types of effects. And that's only because we do so many of these simulations that we can perform this averaging in a very, very powerful way. And what you see on these, the black dots represent the residual uncertainty for the current, or for a set of attenuation relations that are currently being used. And what the colored bars represent are the CyberShake predictions of what that variance should be. How well should those GMPs be able to satisfy, let's say, the CyberShake data set? But it shows you something more. It shows how you can partition that variance into different factors. And you'll notice that above the black curve there, the orange and the red account for about half of that variance. Those are path effects and side effects that we think are much better described by the three-dimensional models, and in principle, we can reduce those to small values. Well, if we can reduce that by a factor of 2, that's the variance. The square root of the variance, which is what this sigma t or standard deviation is, would be reduced at, let's say, at high shaking levels on the order of 1G for this particular site shown here, about a factor of 80. Now that would have a huge impact on risk reduction strategies for critical facilities. Let me give you an example. Pacific Gas and Electric Company owns 60 federally regulated dams in California. Most of those were built in the teens and the 20s, early in California's history. They are not up to seismic safety standards. They estimate to do proper seismic retrofitting on those dams is going to cost them $30 billion. It's one company. And they are stretching that out over 30 years. So they clearly are interested in the reduction of this uncertainty, and we think we can do that with simulations. And whoops, I pressed the wrong button. There, let me get back to this. So in 2015, we've started a project with PG&E and the USGS called the Central California Seismic Project. It's centered around the Diablo Canyon Nuclear Power Plant to test the ability of simulation-based PSHA to lower the epistemic uncertainties. So CyberShake is really a revolutionary model because it provides you with seismic hazard maps, many types of hazard maps, but what is underneath that hood is really amazing. You can drill down into hazard curves for specific sites. You can get hazard disaggregation. You can get individual rupture models. You can get seismograms. And all of these things can be used by engineers in trying to deal with the seismic safety issue. So this shows you a partial list of accomplishments just associated with CyberShake. It's really the first physics-based probabilistic seismic hazard model. It is a leading example of a new program the USGS has on urban seismic hazard mapping. It's being considered by the Building Seismic Safety Council for Project 17, revisions to the building codes. It's been used as a database for machine learning of the California Earthquake Early Warning System, which is currently being deployed on how it would recognize large earthquakes. We don't have the real data for that. We use CyberShake data instead, and that machine learning has been very effective. We've also got pre-computed ground motions that can be used in, for example, short-term earthquake forecasting that is currently being developed as part of the USERF program. Okay, that's pretty good. I think that's suggesting that we're making some significant impacts. But where are we going with this? This shows you the seismic band going from thousands of seconds period down to fractions of a second. As a seismologist, I have primarily in my career dealt with the lower end of that band where we're looking at waves that are propagating through the whole Earth, and we're interested in the whole Earth structure. But if you're an engineer, you're interested in the high frequency part of that band. So you can see that tall buildings are interested in on the order of 10 seconds to 1 second, for houses at frequencies greater than 1 hertz, and in fact for stiff structures like nuclear power plants, you need to go out to tens of hertz. Right now, with our current simulation capability, we can only get out to 1 hertz. So we've got CyberShake to 1 hertz. That's taken a lot of work. As you saw, it took both Blue Waters and Titan to do the calculation for just the Los Angeles region. But we want to push that out to 10 hertz. And to do that, we have to do a lot of things. So there's a lot of new physics we have to put into the problem that is not important at long periods, that becomes important at short periods at high frequencies. And that includes, for example, the roughness of the faults that radiate very complex patterns. They just don't slip like a textbook fault, much more complex. A near-fault plasticity, we have to worry about the frequency dependence of attenuation, which increases above 1 hertz. We have to worry about the details of the topography at the surface and also topography and all the interfaces within the crust. We have to deal with near-surface heterogeneities, small-scale heterogeneities that cause the wave field to be disrupted and decorrelate the waves. We observe strong decorrelation in the seismic wave fields and that is a component needed to describe that, including the fact that the near-surface environment is nonlinear. So I'm just going to show you a couple of recent simulations. This is one done on Titan, which of a fractally rough fault. You're looking at a kind of cutaway through the fault. You can see it's got a lot of topography on the fault. As the rupture propagates, it's generating lots of complicated waves. The one below, however, has got small-scale heterogeneity. You'll notice how the wave fields there are much more disrupted and much more incoherent. And that lower run with the fractal fault geometry really much better describes the wave field than without that. Another issue is the question of nonlinearity of the response of the near-surface environment. That's not just beneath the site, but as the surface waves are traveling along. So this is a replay of the shakeout scenario done at up to 1 hertz, and again done on Titan. You can see the green areas represent regions where the seismic strains are so large that the Earth becomes plastic, and you get plastic dissipation. This can significantly lower the wave field values, but we don't yet know by how much because those parameters aren't calibrated. Now that we have simulations, we can begin to use the simulations and compare them with data to begin that calibration project. So this is sort of a summary slide that shows you the potential, go back one, realized impacts that I've described. I think the Resilience by Design study is a really good example of what can come out of a strong science basis for this type of hazard analysis. But remember, this was just done in 2015. It's based on simulations we did in 2008. So there is a lag between doing the science, getting it out there, and getting it into the public process of improving our resilience and reducing our risk. We've got standards now for California in terms of the earthquake rupture forecast. We think eventually these simulation-based models will become standards. We've already seen that the simulations have allowed us to reduce insurance rates. CyberShakes demonstrated the feasibility of a full physics-based BSHA, and that's going to be very useful for Los Angeles. The question, of course, is how do we move this out into other regions? So in terms of potential impacts, we are, first of all, using these simulations to do distributed infrastructure risk analysis, for example, with the LADWP. We've got the Central California project to look carefully at the reduction of uncertainties. And I should say, on top of all of this, is all kinds of verification and validation activities that I haven't had time to describe. And eventually, we want to move this out to the entire world. To do that, we need, obviously, more computing. And the blue here shows you our current computational scale, and the red shows you where we're going. Essentially, this will scale like computer time. Requires, of course, much more in the way of I/O and storage, but we need exascale computing. So let's go onward to exascale. And I want to thank my colleagues in the organization that participated in this research very much. I know many of you are here, and it's because of the resource providers that we can actually do this very important science. Thank you very much.
Thank you very much for this amazing talk. And actually, the most voted question on is actually, I guess everyone wants to show this great talk to his colleagues at home. Will the slides be available, or is it recorded? So I can actually answer that. Sure. So we are recording the sessions, like both the first talk and that one, and also other invited talks. And then after the conference, at some point, they will be made available at the YouTube channel of the conference in the digital libraries too.
Yeah, I'd be happy to make available to anybody who wants them the animations that are shown here, plus we have many more, and the view graphs themselves if you'd like them.
Is there anyone, you can use the microphones. Otherwise, I have like one question. So you said like onto exascale. Do you see like exascale would be enough, or do you already see a need for going beyond exascale?
Well, you know, these problems obviously scale up. I mean, most of what I showed you applied to Southern California. Southern California is a pretty small postage stamp on the face of the planet. There are many other seismically active areas, and to move this technology into any one of those areas, you've got to go through all of those computational pathways that I showed you. You have to develop models of the fault systems. You have to understand the three-dimensional structure of the Earth. That requires large-scale computing. And then, of course, you want to calculate the actual hazard maps themselves. So, you know, when we first started on this, people said, come on, George, no way. There's no way you're going to be able to to do these kinds of calculations. But of course, that was before. That was when we were just at terascale. Now that we're at petascale, we can really start to bring home the bacon. And at exascale, I think we'll be able to solve a lot of problems that we've been wanting to solve.
Okay, we have time for one quick question.
Jack Wells, Oak Ridge, terrific talk. Could you comment on the challenge of coordinating these large, diverse, national-scale resources of people, networking, compute, and data? How do you pull all this together?
How do we pull it all together, or how should we be able to pull it all together? Well, you know, at the risk of showing another slide, we do actually have to be able, you know, these require large software engineers, and we have to get the resources, both the compute resources and also the software engineering resources. I think it's back on. So clearly, I'm hoping that the National Strategic Computing Initiative will help us in terms of solving those problems.
Okay, so thanks again, Dr. Jordan, and thanks again for coming.